One of the first things we want to learn about as we develop our skills in calculus is the concept of the derivative. Derivative is a mathematical operator that helps us understand the techniques for calculating the slopes of lines tangent to a curve. For example, if you remember the idea of average velocity, the average velocity is defined to be the change in the position of an object with respect to the change in time. So it's just how far some object has traveled and how much time it took to travel, and the ratio of the two is the average velocity. Well, graphically, we can notate that as a line segment in between 2 points on a position time graph. And it looks like the slope of that line segment. Take a look. So if this is the position function here, and this is the time axis like this, we could see a position function. Maybe it looks like a parabola. And if you start at some particular time right here, and then you go to, from that position, you go to some other position, and that position is about right here, and that corresponds to this amount of time. What you've done is you sort of created this secant line that goes from here to here. And that secant line has a slope that is essentially just the change in the position over the change in time. So all this down here is the time that passed, and this over here is just the distance that the object traveled in the direction that it traveled in. So this secant line here is V average. So what the derivative is allowing us to do is to consider not just the average velocity between 2 points in time, but the instantaneous velocity at a particular point in time. What is the instantaneous velocity right there at that particular time? Or say that's time 1. Or as the object speeds up, notice that the slope of secant lines would increase. So I might ask, what is the instantaneous velocity at that particular time point in time t2? Let me show you a different way of looking at this. This is Desmos. It's a web-based graphical calculator that works really well for visualizing this kind of situation. So I've graphed a parabola here, and the blue parabola represents the position function. And if I turn on the secant line, that red line there represents the average velocity between 2 positions in space, so between 0 meters and 8 meters in space, and between 0 seconds and about 9 seconds in time. So what I'm interested in is not just the average velocity between those 2 points in space, but say the instantaneous velocity right here at 5 seconds. So what I can do is I can bring this point here closer to 5. Maybe I'll put it to 4 seconds, and I'll grab that other point and bring it to the other side of 5 seconds, say 6 seconds. And now what I'm getting is the secant line in between 5 and 6 seconds. Let me see if I zoom in there. Keep the window looking normal. The origin at the, there we go. So I'm looking here at the average velocity between 4 and 6 seconds. This is right in the region of that 5-second mark. But I'm still getting this secant line. So it's the average velocity between 2 points in time right around 5 seconds. My goal is the instantaneous velocity at 5 seconds. So I'm going to conceptually just move this to say 4.5 seconds and move this point to 5.5 seconds. And it looks as though the secant line is right along the same line as the position function. So if I zoom in, what you see is I'm not quite there. The secant line around 5 seconds is not quite the same as the slope of the line right at 5 seconds. So I'm going to do something similar. I'm going to bring this point right before 5 seconds and bring this point right before 5 seconds like this. So I'm like zooming into the 5-second mark like this, about a half second on either side, or something 1/10 of a second. Let's see what happens. Zooming in, zooming in, zooming in, zooming in, zooming in, zooming. Oh my gosh, look. I'm still not quite there. So the concept of the derivatives is really just allowing us to consider the secant line around a point on a graph that's really just getting closer and closer and closer to the line tangent to the function right there. And you can see I just keep zooming in, zooming in, zooming in, zooming in. There it goes. I can do this all day. So we have a mathematical way of doing this where the secant line gets to be closer and closer and closer to the slope of the tangent line right there at that 5-second mark. So let me show you the concept. We begin by writing out exactly what we're interested in. The instantaneous velocity as a function of time is equal to the secant line between 2 points in space and time that are infinitely close together. So I'm going to write this out as the position at time 2 minus the position at time 1, all divided by the difference in time t2 minus t1. And that's a lot like this. It's just an expansion of that. But the exciting part is that we're going to consider what happens when the time interval between t2 and t1 gets infinitely small. So we're zooming in onto essentially time 1 and letting time 2 get closer and closer and closer to time 1. And to do that, we're going to invoke the limit. So what I've written here right now is still the average. But as I step back, and I'll write the vector notation now just to keep everything formal. But let's zoom out before we zoom in and look at the instantaneous velocity. Here's the big deal, the big difference. The instantaneous velocity is equal to the same idea, the difference between these two positions and these two times. However, now I'm going to include this new idea. The new idea is in the limit as the difference between time 2 and time 1 approaches 0. We're letting the difference here get infinitely small, but not be 0. Time 2 cannot be time 1. It has to be some small amount away. And so when I rewrite this, it turns into, so this is the instantaneous. Instantaneous. It's instantaneous velocity. So here we go, rewriting this. Let's just look at the formalization. We'll say t2 minus t1 equals delta t. And so I can look at this as t2 is t1 plus delta t. That's a way to think about that. So we're going to pretty much write t2 like this from now on. And delta t is going to be this smaller and smaller and smaller and smaller interval in time that separates out time 2 from time 1. So when I write this out formally, it'll say v as a function of time. The instantaneous velocity is now in the infinite limit as the time interval delta t approaches 0. That's the time between here and here. That's delta t. It's going to be the position function evaluated at t1 plus a little bit of time to get me to time 2 minus the position function evaluated at t1 all over delta t. So that big idea right there is sort of the basis of the derivative. It's the formula for the slope of a secant line that is between 2 points that are infinitely close together. Well, I think we should apply this to something that we already know the answer to, just to see how this works, right? So let's assume that we're looking at an object under uniform acceleration. like we did in our regular physics or AP Physics 1 class. So let's say that we have a position function x as a function of time is some initial position plus some initial velocity times time plus 1/2 a constant acceleration times time squared. Now that graphs as a parabola, and you might recall that the instantaneous velocity as a function of time was v0 plus a t. So we know this is the result of the derivative operator applied to this position function. Okay, let's go through the mechanics of doing that work, figure out what the derivative is. So let's keep in mind what we're trying to do is to find the slope of the line tangent to the position function. So I'm just going to draw that really quick. I think it's important to visualize what it is we're trying to do. It's easy to lose track for sure. So here's this parabolic position function. And we're trying to find the slope of a tangent line right at some particular point. Say right there. Okay, so that's what we're interested in doing, is finding the slope of the tangent line right at that particular t1 value. Right. So let's write it out. The instantaneous velocity is equal to the limit as the time interval between t1 and t2 approaches 0 for the slope of the secant line between the position at t plus a little bit more time, which would be t2, minus the position at t, all divided by change in time. Seems pretty simple. And all we have to do now is just apply the position function that we're interested in finding the derivative of, or that is to say, apply this rule to the position function whose slope of tangent lines at any particular point we're interested in finding, because the slopes of those tangent lines represent the instantaneous velocity. Right? That's the instantaneous velocity right there. So I look up here and I see the position function is defined like that big dog displacement equation. So it's x0 plus the initial velocity, t plus a little bit more time to get to time 2, plus 1/2 a time plus a little bit more time squared, minus x0 plus v0 t plus 1/2 a t squared, all divided by a little change in time. Close that bracket here. So this first bunch of stuff, and this first paren, you want to think about it like that, that's the position function evaluated at a little bit more time, t2. And this is the second bunch of stuff, is the position function at the original time, t1. I just take the difference between those two positions and divide by the time between those two positions. No big deal, seemingly. But it just keeps going. The hardest part about calculus is the algebra. So let's just work out the algebra here. Delta t approaches 0. Keep a big bracket. So x0 plus, here's v naught times t, distribute, times delta t. I've just distributed here and distributed there, plus 1/2 a. And now I've got this binomial I have to work out here. So this is going to be foiling the binomial, t squared plus 2t delta t plus delta t squared. Now I'm here at the negative sign, so there's the negative sign. Then that negative distributes through this trinomial. So I get x naught minus v naught t minus 1/2 a t squared. And all of that, let me try it this way. All of that is over delta t. Close that bracket and do some more. Copy it along with me. Work a little bit ahead and check your work against mine. I'll send you these notes at the end of this lesson. I'll give you my practice page. Plus v naught delta t. It's just transcription. Now here goes. I need to distribute this 1/2 a to each of the terms inside this trinomial. So the first one gives me a 1/2 a t squared plus, and the 1/2 and the 2 cancel, so I'll get just a t delta t, and then plus 1/2 a delta t squared minus x naught minus v naught t minus 1/2 a t squared. I'll close the brackets and divide by delta t. Continue to reduce. See if we can combine some terms together. Got my limit. As delta t approaches 0. My bracket. Well, this x naught term and the minus x naught term, those add together to be 0. This v naught t and the minus v naught t add together to be 0. Here's a 1/2 a t squared and a minus 1/2 a t squared that add together to be 0. So I'm going to reduce again to just end up with v naught times delta t. That's this term here. And I've got this term plus a t times delta t. I've got this term plus 1/2 a delta t squared. And all of that is over that super small change in time that's going to approach 0 in just a moment. Let's see if we can do any more algebra. So I can form some ratios here. Each of the trinomial numerators can be put over that delta t denominator. So v naught delta t all over delta t plus a t delta t all over delta t plus 1/2 a delta t squared all over delta t. And this is an interesting argument here. Delta t will never be 0, so I'm never dividing by 0. It's always some number greater than 0, but infinitely close to 0. So before at any time that I want to imagine delta t approaching 0, the ratio here of delta t divided by delta t will always go to 1. And this ratio of delta t to delta t, no matter what delta t is, since it will never be 0, that ratio will always be 1. And I can cancel one factor of delta t here with a factor of delta t there. And we're almost here at the end. And I'm just about to consider the actual limit as delta t approaches 0. After all this time. Pun intended. So I have v naught plus at plus 1/2 a delta t. So now let's consider finally what happens in the infinite limit as the time interval between time 1 and time 2 on our graph up here. Where was it? Here it was. There it is. As the time interval between time 1 and time 2 gets infinitely small. So these 2 points get infinitely close together. We're looking at that secant line right there. Delta t is essentially 0. Not 0, but infinitely close to 0. So 1/2 times a times something that's almost 0. This term gets infinitely small and approaches 0. And so the result of our derivative is that the instantaneous velocity will be equal to v0 plus at. Now this is an equation that predicts the slope of lines tangent to that position function at any time t. It's amazing. It's super powerful. And this happens again and again and again as we study calculus-based physics. It's not just this position function that this is useful for. It's all kinds of other functions. I can't wait to show you. So let me write this as the instantaneous velocity. Turns out there's a shortcut to do this as well. You don't have to work through all this algebra every single time. And that's going to make it much easier to find the slopes of tangent lines to functions as we go on. And I'll show you the shortcut soon.